Hello and welcome. In this video lecture, we're going to begin our series on mathematical preliminaries for the topic of engineering design optimization. And the first topic we're going to start off with is linear algebra. In this lecture, we're going to start off with a brief review of topics from a first course in linear algebra, a prerequisite course. And these are things that should have been covered in a previous course and that you need to be familiar with. Second, we're going to dig into this topic of quadratic forms. This is something that some of you may have seen before, but others of you may have not. We're going to touch briefly on matrix transformations, eigenvalues and eigenvectors, and specifically in a way that relates to what we need for a foundation of optimization. We're going to talk about diagonalization, characterization of quadratic forms, and then finally, matrix definiteness. Let's talk about some of the topics you've probably seen before, but that if you don't have fresh knowledge of, you should probably get more familiar with. In this lecture, we're going to cover some of the really essential linear algebra topics that are not always covered in a first course, other than the quick review of some of the topics you may have seen before. There are a number of resources that you can go to in refreshing your knowledge of linear algebra. You can go to the course notes on mathematical preliminaries. There's both the handwritten notes, and then there are also some other notes that are available to you. You can go to the main textbook, Chapter 2, and also if you have the textbook from your previous linear algebra course, which is a prerequisite for this class, you can go back to that textbook to refresh your knowledge of these topics. Some of the topics you need to know include the dot product, sometimes known as the inner product or scalar product, and related to that, the topic of projection. You need to understand matrix algebra, not just addition, subtraction, and multiplication, but also things like transposes and identities or different properties in matrix-based calculations, matrix-based algebra. You need to understand what matrix determinants are and what the properties of determinants are, including how they behave in different algebraic calculations. You need to understand a range of different special matrices and their properties, including symmetric, skew-symmetric, orthogonal, and triangular matrices, as well as diagonal matrices. You need to understand matrix inverses, and in addition to the importance of matrix inverses with respect to mathematical development, you should also be aware of the numerical issues that are connected with matrix inverses. You need to know what eigenvalues and eigenvectors are. In this lecture, we're going to go through these topics in a little more depth, but in a specific way that should give you some helpful perspective that is important for optimization theory, and then some other topics as well. You need to know what matrix diagonalization is, also coordinate transformations and eigenbases. Okay, now we're going to switch over to the drawing pad, and I'm going to work through the topics that are covered in the mathematical preliminaries notes, specifically for linear algebra. Let's start off talking about the topic of quadratic forms. And to begin, I'm going to introduce a simple example, a quadratic function. This is a function of two variables. Here I show the vector x that includes two components, x1 and x2. And this function is a function of x1 and x2. It includes both linear and quadratic components. And I'm going to use this to describe a more general form of quadratic functions. We can write this function equivalently in a matrix-based form. If we have a look, for example, at these first two terms, these are linear terms. This is going to be equivalently equal to 1 times x1 plus 2 times x2. And if we think about vector multiplication, then we can rewrite this in this way. This row vector 1, 2 times this vector x1, x2, that's going to be equal to 1 times x1 plus 2 times x2. So that is equivalent to these first two terms. And then we can write the quadratic elements here using matrix multiplication. Here I'm going to take the transpose of the vector x, and then we're going to multiply it by a matrix and then by the vector x. So the trick is to figure out what are the components of this matrix such that when we multiply this out, it's going to be equivalent to these two terms that are the quadratic terms for this quadratic function. And I'm just going to write these out here, and it's really pretty straightforward the way that I've written this. And here we only have an x1 term and an x2 term. There's no term that involves a combination of x1 and x2, or in other words, there are no cross terms, and these cross terms show up in this matrix as diagonal terms, or sorry, off-diagonal terms. So in this case, our components then are just 3, 0, 0, 4. And when we are creating a matrix for a quadratic equation like this matrix is always going to be symmetric. If we only have terms involving a single variable squared, then it's going to be a diagonal matrix. All of the off-diagonal terms are 0. But if we had any terms that were x1 times x2, for example, then we would have some non-zero off-diagonal terms. Let's think about the general form that this expression takes. We can rewrite this as a vector A transpose times the vector x plus x transpose times a matrix B times the vector x. This is the linear term. This is the quadratic term. And if we were to go back and plug in the values up here and then perform the matrix multiplication, we would see that it would result in the exact same quadratic function. Now, if we are talking about quadratic forms, this specifically refers to functions that only include this quadratic term. And quadratic forms are really foundational to some of the derivation of optimality conditions, to understanding the nature of nonlinear optimization, and also to numerical algorithms for optimization. Let's talk about matrix transformations. This is one of the first topics that you learn in a class on linear algebra, and it's primarily about what happens to a vector when we multiply it by a matrix. Suppose we have a vector I'm going to call A, and we pre-multiply it by a matrix capital A. Suppose we have a dimension of A of length 2, and then A is a 2 by 2 matrix. So then we're going to have this 2 by 2 matrix multiplied by a 2 by 1 vector, and the result is going to be another 2 by 1 vector. And so we're inputting a length 2 vector and we're outputting a length 2 vector. So this could be viewed as a transformation of a length 2 vector. So what does this matrix multiplication do to this vector? If this vector has length 2, then we can visualize it. Suppose we are looking at a space of 2 dimensions and we can visualize a vector of 2 dimensions somewhere in this space. The vector A can be visualized as a point in this space or as a vector pointing from the origin to the point A. And then if we multiply this vector A by a matrix capital A, there are a number of things that could happen. I'm going to define A hat as the output of the multiplication capital A times A. And in this case, there are 2 things that happened. The length of the vector was reduced. So there was a scaling or a magnitude effect. But in addition to reducing the length, there was a rotation. We rotated the vector by some angle theta clockwise, at least the way I've represented it here. And there are ways of defining the magnitude of the length reduction or increase, and also the rotation. And I would encourage you to go back to your linear algebra course and review some of the rules of rotation and magnitude changes or scaling that can occur due to matrix multiplication or matrix transformation. Let's talk about eigenvalues and eigenvectors. This corresponds to a very special case when we are performing matrix transformations using a special vector. Suppose we have a vector v, and then we multiply it by a matrix A. If v is an eigenvector of matrix A, then it gives us a very specific matrix transformation. It gives us as output the vector v again multiplied by some scalar. So what does this mean in terms of matrix transformation? We can think about visually what this matrix transformation entails. Let's look at a few different examples. Suppose in this 2-dimensional space I've drawn out the vector v, or the point v, or in the vector that points from the origin to this point v. There are a number of different types of transformations that could occur if A and V correspond to this matrix and eigenvector pair. And remember, this quantity lambda, that's a scalar. It's not a vector. It's not a matrix. Well, one thing that could happen is something like this. What if lambda is a scalar that's equal to 2? And then that means AV is going to be equal to 2 times V. 2 times V, that's going to be pointing in the same direction. It's just going to be twice the length. And so this is going to be equal to, this point is going to be equal to AV, or 2 times V. Eigenvalues can also be negative. So what if lambda was equal to -1? In that case, we would have a vector pointing the opposite direction. A times v is equal to -v. Another possibility is we could have a 0 vector resulting. If we had lambda equal to 0, then this would give us AV is equal to 0, and then it would just be right here at the origin. Another possibility, the final possibility, is that eigenvalues can be complex. In other words, the eigenvalue can have both a real part and an imaginary part. these are important properties of eigenvalues. We're going to learn throughout this course that for most of our purposes, we are actually not going to be dealing with this case, where the eigenvalues are imaginary. And that has to do actually with quadratic forms. We're using quadratic forms as models throughout many parts of this class. And we're going to see that because of the properties of the matrices involved with quadratic forms, we are not going to have this case where we have imaginary values for eigenvalues. So suppose we have a matrix with dimension n by n. It's a square matrix of dimension n. It can have up to n linearly independent eigenvectors, v. And each of these eigenvectors, of course, has a corresponding eigenvalue. These eigenvalues for a matrix, say if it's a n by n and we have n eigenvalues, then those values could all be distinct, or we could have repeated eigenvalues. And we're going to be exploring some of the ways that eigenvalues and eigenvectors can help us to understand the properties of quadratic forms and other things related to optimization theory and optimization algorithms. Something to point out at this stage is a really helpful MATLAB command, just spelled EIG, and if we use that and use as the input argument a matrix, this is going to calculate both the eigenvectors and eigenvalues using some really fast algorithms that numerically identify these eigenvalues and eigenvectors through some very efficient algorithms. Now, we're going to just review briefly how we can do this symbolically. This is something you need to know how to do, but it's not going to be a focus of the course. Suppose we want to find the eigenvalues of a given matrix A, and suppose that the matrix A is dimension n by n. The way we do that is we form this new matrix, which is equal to lambda, which is what we're solving for, times the identity matrix, which is the same dimension as A, so that this is a consistent expression. And we take this matrix lambda I, the identity matrix, minus A to form this new matrix, and then we take the determinant of that matrix. We are going to have still this unknown lambda, and this is going to form what's called the characteristic equation or the characteristic polynomial. And then we're going to use that to solve for lambda. There are going to be multiple possible solutions, and we can have, as I mentioned before, distinct solutions, distinct values of lambda that satisfy this characteristic equation, or we could have repeated solutions or repeated roots for this equation. As we discussed previously, eigenvalues could be zero, they could be complex, they could be repeated, or they could be real distinct values. A matrix that is dimension n by n has at most n distinct eigenvalues. Now, if we have some number of distinct eigenvalues m that maybe is less than n, then we can have at most m linearly independent eigenvectors. If we have the case where m equals n, where m is the number of distinct eigenvalues, then there exists what we call an eigenbasis. Now, thinking back to what you've learned in linear algebra, a basis is a set of n linearly independent vectors that spans Rn. So what does it mean to span Rn? That's something to go back and make sure that you recall. The basis also can be used as a coordinate system for Rn. And when I'm saying Rn, I'm talking about the space of real variables, real quantities of dimension n. Specifically, an eigenbasis is a basis where the coordinates point in the directions of the eigenvectors. Now, we're talking about coordinate systems here, and this is something that I hope you've encountered before. If it's something that is not too familiar with you, please go back to your linear algebra materials and review what an eigenbasis is and what coordinate transformations are. Another important property is that if we have this case where the number of distinct eigenvalues is m, and m is equal to n, then we can say that the matrix A is diagonalizable. This is a really useful property. Understanding diagonalization of matrices and the results that we're going to discuss here is really essential for both optimization theory, being able to define optimality conditions, in other words, and also for the numerical methods that we're going to be deriving for optimization. There are three things that are essentially equivalent. If we are able to diagonalize a matrix, then that means that we have these m equals n distinct eigenvalues, and also that the eigenvectors form a new coordinate system for us, and that's going to be an eigenbasis. So let's go back to this concept of diagonalization. There's a specific way of diagonalizing a matrix that utilizes the eigenvectors associated with a matrix. So just as a reminder, if we go back to this earlier equation where AV is equal to lambda V, and we here are saying that V is a special matrix that's an eigenvector, sorry, not a special matrix, a special vector, that's an eigenvector associated with the matrix A. By definition, the eigenvector is one where if we perform a matrix transformation using A on the vector V, it does not rotate the resulting matrix. It only scales it. So if we have a matrix A, and if we have an associated set of eigenvectors, and if m equals n, and we have n distinct or n linearly independent eigenvectors, we can take all of those and define a special matrix. I'm going to call it S, and this is going to be an n by n matrix, and I'm going to define it as the concatenation of these column vectors v1, v2, all the way up to vn, where each of these is one of the eigenvectors associated with the matrix A. And if m equals n, then that means that each of these eigenvectors is linearly independent. And if we were to take this matrix and pre and post multiply A, it will give us a very special result. I'm going to say that this matrix D, which is a diagonal matrix, is going to be equal to the inverse of S, which is the concatenation of the linearly independent eigenvectors, times A times S. But so it turns out if we go through this multiplication and determine what this matrix D is, it is diagonal, which means that all of the elements that are not on the diagonal are 0, and the elements that are on the diagonal are special values. And those values on the diagonal are the eigenvalues. So lambda 1, lambda 2, all the way up to lambda n, and then all of the off-diagonal terms are 0. Let's use that information to understand transformation to different coordinate systems in a way that's going to give us some new insights for understanding quadratic forms or quadratic functions much better. Now, specifically, a quadratic form, it only involves this quadratic term. Earlier, we looked at a more general quadratic function that had both a linear term and a quadratic term. If we don't have the linear term, then that produces some special properties. It's the linear term that allows us to shift the function around or away from the origin. If we think of a quadratic function, say it's either a parabola or hyperbola, well, the minimum or maximum for a parabola, in this case, if we don't have a linear term, if it's a quadratic form, then it's going to be right at the origin. Let's have a look at what the level sets or the contour plot of a function might this look like. Here I've drawn the level sets for a response surface that is parabolic in shape. And we can specify a point in this space using the coordinate system x. Suppose this is a point P. And if I look at a projection of this point on each of the coordinates x1 and x2, if we look at these projections, then we can use those projections to define this point in this coordinate system x1, x2. This applies to spaces of more than 2 dimensions as well, but for visualization, we're looking at 2 dimensions. So suppose if n equals 2, we have a quadratic function in general that looks like this. And then if I were to write out each of these components in more detail, it would look like this. Now, if the matrix A here is symmetric, and that's actually an important property of quadratic forms. The matrix A that's used to define quadratic forms is symmetric. Then we can take this and rewrite this function, multiplying everything out. That's going to be equal to a11 times x1 squared plus a12 x1 x2, but then if it's symmetric, if a12 is equal to a21, we're going to have 2 of these terms, so I'm just going to multiply that by 2, and then we're going to add the last term, a22 times x2 squared. Now, make sure that you can multiply this out and everything makes sense. Now, this term actually produces some interesting effects. This is the cross term. It's because of this cross term that we get what we call correlation. If a12 or a21 is not equal to 0, then we get this behavior where x1 and x2 are correlated. In other words, the value that x1 takes on will influence how much x2 will change the output f of x. And the converse is true. The value of x2 is going to influence how much influence the change in x1 has on f of x. We say that these variables are correlated, or that they interact, in other words. Now, these terms, these correlation or off-diagonal terms, these are the things that are not on the diagonal. If we have any non-zero, non-diagonal terms, we get this kind of this correlation behavior. And one way of thinking about that graphically is that the coordinate axes, say here x1 and x2, are not going to be aligned with the minor or major axes of the conic sections, the ellipsoids, or the hyperbola that form the level sets of f of x. So if I go back over here and I think of these level sets as a set of aligned ellipses, then if I were to draw the direction of their major axes and their minor axes, those directions are not going to be aligned with x1 and x2. So that's the case when we have any off-diagonal terms that are non-zero. We're going to have this sort of rotation between the coordinates and the directions of the minor and major axes. Another way of looking at this is if we see a function, a quadratic function, where the level set ellipsoids are rotated, they're not aligned with the coordinate axes, then we can say that the matrix for the quadratic term is non-diagonal, and at least some of the variables in the vector x are correlated. Another way of describing this is that these variables x are not independent. Or in other words, the influence of x1 on the function f of x is dependent on x2. Because we don't have independent variables, it's really hard for us to make any general statements about the nature of the function. We'd really like to make some more general statements about the nature of this function. If we're trying to derive more general things like optimality conditions to know whether for sure we are at a minimum or a maximum, we need to be able to make some general statements. We're going to learn about three equivalent things. One is coordinate rotation, diagonalization, and then also forming a new coordinate system using the eigenvectors of a matrix A. And we're going to see that each of these three things are equivalent. To summarize, we're going to look at how we can rotate the coordinates such that they will line up with the axes, or the minor and major axes of the level sets of the quadratic function. So in other words, say if I go back to this figure here, if I were to rotate these axes by this amount, theta, then the axes would be aligned, and then we get this nice property of independence between the different variables. And then that's going to allow us to make some more general statements about the nature of this quadratic function. And we're going to see that this is equivalent to diagonalizing the matrix A, or, in other words, forming a new coordinate system using the eigenvectors of the matrix A. When we do this, when we rotate this coordinate system and the coordinates are aligned with the minor and major axes of the conic section, then we're not going to have any of this correlation. The variables are not going to interact, and then that means we're not going to have any of these off-diagonal or cross terms. And if we have zero off-diagonal terms, then that's going to produce a diagonal matrix. Suppose I use the symbol C to represent the new coordinate system. C sub I is the ith coordinate of this new coordinate system, and if we are starting off with a dimension n coordinate system, we need to maintain a coordinate n or a dimension n coordinate system. This is going to be the minimum number of coordinates required to have a linearly independent coordinate system that can span the whole space of dimension n. If we were to rotate the coordinate system such that these new coordinates point in the same directions as the eigenvectors the v values. Then we can redefine the quadratic function f of x in terms of this eigenbasis. So let's redraw this for a little bit of clarification. Suppose again we have a two-dimensional function and the original coordinates are x1 and x2. And we have interaction between x1 and x2 such that the minor and major axes of the ellipses from the level set of the function f of x are not aligned with the coordinate axes. But then here we want to rotate the coordinates such that they are aligned, and those new coordinates are going to be c1 and c2. Suppose we have a point P in this two-dimensional space. We can project this point either onto the original coordinate system, x1, x2, or onto the new coordinate system, c1, c2, and we're defining the same point just in two different coordinate systems. You might be able to see how aligning the axes with the eigenvectors is going to be convenient for some things. But to make use of this, we need a convenient way of mapping or transforming between the coordinate systems. So suppose we have a point P, and we can define it in the x-coordinate system, or we can project it onto the c-coordinate system, and we need to define it in either case. So here in the x-coordinate system, the first x component will be this magnitude, this length, where P is projected along x1, and then the second component will be this magnitude, how far P is projected along x2. But then if we look at the c-coordinate system, c1, the first component, c1, that's going to be this length, that projection onto c1, and then the second component is going to be this length, the projection onto c2. Suppose that we are looking at an eigenvector of matrix A, vi, and we are visualizing it in the x1, x2 space, and we can express it in terms of the x coordinates. But then suppose we have a position ci along this ci coordinate axis that is aligned with the coordinate system. We can then define the vector x as being equal to ci times vi, where vi has two components. Or more generally, we can define an arbitrary point defined in the new c-coordinate system using a value for each of the c coordinates. And we can rewrite this, we can combine this result with this result, and we can write that a general point x in the x-coordinate system is going to be equal to the scalar value c1 times v1 plus the scalar value c2 times the vector, the eigenvector v2, all the way up to cn times vn. Now, if we conveniently go back to the matrix S that we defined earlier, which is the concatenation of all of the eigenvectors into a single matrix, then we can take this expression, this way of defining x in terms of the eigenvectors, and simply just write it as S times the vector c, where the vector c is defined right here. So if we are wanting to map back and forth between the x-coordinate system and the c-coordinate system, we can look at it this way. if we were looking over here that x is equal to s times c, suppose we have a point defined in the c coordinate system. If we pre-multiply it by s, then that gives us x. So transforming from the c coordinate system to the x coordinate system is as simple as obtaining x from s times c. But then how do we go the other direction? Suppose if we have a value for the vector x and we want to get a value for the vector c, then we can just use the inverse of the matrix S. So we get c is equal to the inverse of the matrix S times x. Now let's wrap everything together and learn how we can rewrite a quadratic form in terms of the new coordinate system. In other words, if we're starting off with a quadratic form in the x-coordinate system, how do we rewrite that quadratic form in terms of the new c-coordinate system? Now remember this relationship. X is equal to s times c. If we just do a simple substitution, I can write that f of x is equal to f of s times c. And if I do a substitution and replace x with s times c in the formula for a quadratic form, and here I will just write that out briefly to make this clear, x transpose a times x, and then I substitute in s times c for x, sc quantity transpose times a times sc. And then if I multiply all of this out, we can simply just rewrite it using identities of linear algebra as c transpose s transpose a s times c. And S, it turns out, is an orthogonal matrix. It's composed of eigenvectors. And if it is an orthogonal matrix, we can write that the inverse of S is equal to the transpose of S. So therefore, this is equal to C transpose S inverse times A times S times C. Now there's some interesting things here. We're going back to the definition we derived earlier regarding diagonalization of a matrix A. Remember, this diagonal matrix where all of the eigenvalues, or it's composed of the eigenvalues on the diagonal of the matrix and everything else is 0, this is equal to the inverse of S times A times S. So therefore, this middle part of the expression is equal to D, or in other words, the quadratic form in the new coordinate system is equal to C transpose times D times C. This is an important result, and this is actually going to really provide some deep insight into the nature of the shape of quadratic functions in terms of eigenvalues and eigenvectors. With this definition, remember that the eigenvalues are on the diagonal of this matrix D, and we can now rewrite f of x in a very specific way. That really is an exciting result. F of x is equal to x transpose ax, but it's also equal to c transpose d times c. So what is c transpose d times c? Well, d contributes a lambda to each term. So for the first term, we get lambda 1. And then the c vector on either side is going to contribute a c squared to each term. But because the matrix D has no off-diagonal terms, we are going to get no cross terms. If it helps, go back, say with just a 2x2 example and multiply this out to make sure that this makes sense to you. But in a general n-dimensional case, we're going to get this expression for f of x, where we have lambda 1 times c1 squared plus lambda 2 times c2 squared all the way up to lambda n times cn squared. One of the key observations here is that in this way of defining f of x, we have no cross terms. If we transform our coordinate system from x to that of c, which is in the direction of the eigenvectors, then we have no cross terms. There is no correlation between the variables. The variables are independent, or in other words, if we look at one of these variables, if we look at, say, c2, if we change c2, it is going to influence f of x in a particular way, no matter what the values of c1, c3, all the way up to cn are. These are independent variables. And this helps us to understand the nature, the shape, the characteristics of this quadratic function in a much more general way. If we increase or decrease one of these quantities, say c2, it's going to change f of x quadratically. Another key observation is that the sign of the corresponding eigenvalue is going to tell us how changing the corresponding coordinate is going to influence f of x. So if lambda 2 is positive, if I increase c2, then that's going to increase f of x quadratically. If lambda 2 is negative and I increase c2, actually if I increase or decrease c2, if I just increase the magnitude of c2, and if lambda 2 is negative, then that's going to decrease the value of f of x. The magnitude of the eigenvector tells us how rapidly the change is going to occur. So if I have a really large value of lambda 2, then movement in the c2 direction is going to cause a really significant, a very rapid increase in f of x. However, if we have a really small value of an eigenvalue, say lambda 2 is close to 0, its magnitude is close to 0, then changing c2 in that direction is going to have very little influence. A way of thinking about this geometrically is that for directions, for eigenvector directions where the corresponding eigenvalue is large, moving in that eigenvector direction, we're going to have a very steep change in f of x. We're either going to have a very rapid increase or a very rapid decrease. But if we have a small eigenvector in the direction of the corresponding, or small eigenvalue in the direction of the corresponding eigenvector, say if it's close to 0, then if we move in that eigenvector direction, that coordinate direction, then it's going to be fairly flat. We're going to have not a very large increase. So this geometric insight that is built on this analysis from linear algebra, it provides us a way to understand the shape of quadratic functions in a really general way that extends beyond 2 dimensions. We can go to n dimensions, an arbitrarily large number of finite dimensions. And by understanding the values of the eigenvalues, we can say something about the nature of this nonlinear function. As we keep going in this class, we're going to be using quadratic functions as a model for nonlinear functions. And if we're looking at points that are really close to the origin of the quadratic model, then we're going to have pretty good accuracy. And then this is going to be useful for saying things about, say, optimality. So these are some really foundational results. Let's have a look at an illustrative example. Let's suppose we are operating in R2 the number of independent variables is 2. And suppose that lambda 1, the eigenvalue associated with the first eigenvector, is larger than lambda 2, and they both are positive. And let's suppose that C1 and C2 point in the direction of the minor and major axes of the level sets. And because lambda 1 and lambda 2 are positive, then that means we are increasing, or say if we start at the origin and we move in the C1 direction or we move in the C2 direction, then that means that the function value f of x is increasing. So suppose we are assuming again a quadratic form where the function f of x is equal to x transpose a times x. So because of the properties here where the eigenvalues are both positive, we're able to say, and actually we'll be able to show this as a very general result in any direction. It doesn't matter. Any direction that we move away from the origin, our function f of x is going to be increasing. So you might be able to see how this relates to optimization now, in that we can, it's possible to prove that at the minimum here, or sorry, at the origin here, we have a minimum of the function f of x as opposed to a maximum. In other words, the values, the signs of the eigenvalues here, they give us some understanding of the shape of this function. Because they're all positive, we have a concave up function or a convex function. If we are moving in one of these coordinate directions, say the C1 direction, the value of the corresponding eigenvalue, lambda 1, gives us a sense of how steep it is. So I've ordered these in a particular way. I've said that lambda 1 is greater than lambda 2. If lambda 1 is greater than lambda 2, then that means if we move in the C1 direction, the function f of x is going to increase more rapidly than it does in the C2 direction. And the way I've sketched things out, that agrees with this arrangement. If we move in the C1 direction, the space or the distance between the level sets is smaller than the space between the level sets moving in the C2 direction. And so therefore the steepness in the C1 direction is greater than the steepness in the C2 direction. If you have any familiarity with topographic maps, say trying to visualize what mountains or hills look like, then this will make sense to you. If you have lines on your topographic map that are really close to each other, then that corresponds to very steep terrain, whereas if you have lines that are very spread out, then that corresponds to very mild or fairly flat terrain. So one of the takeaways here is that the quantity or the value of the eigenvalue corresponding to an eigenvector tells us how quickly f of x is increasing. So it's helpful to think about, well, what happens if we have different relative sizes, different relative magnitudes for these eigenvalues, and we can think about the different possible shapes that could emerge. So for example, if lambda 1 and lambda 2 were both negative, then what does that tell us about the shape? If we are moving in either the C1 or C2 direction, and both eigenvalues are negative, then that means f of x is going to be decreasing as we increase either C1 or C2. So that means we have a concave down function, and then the origin is going to be a maximum instead. In the notes for these mathematical preliminaries, I have a few exercises for you to think through where we're looking at different values and signs of eigenvalues for a quadratic function of two variables. And I encourage you to think through all of the different possible combinations of signs and relative magnitudes so that you can gain some confidence in the intuition that these values give you for the shape of these functions. So here are two of the examples that I gave. Here we have lambda 1 equals 1,000, lambda 2 equals 0.1. And that's really similar to what we saw over here, except the relative steepness between the two coordinate directions, C1 and C2, is even more exaggerated. So we have a 10 to the 4th difference in magnitude between the steepness of those two different directions. And if we were to visualize that, then these level sets would be super skinny. We would have this very different sort of shape compared to what I illustrated originally. Now, if we look at case C, the magnitudes are pretty similar, but we have different signs. So that means if we move in the C1 direction, we are increasing. If we are moving in the C2 direction, we are decreasing. So what does that mean? What does that mean about the shape? Say that's x1, that's x2, that's c1, and that is c2. So with the direction c1, we're going to be increasing, but then the direction c2, we're going to be decreasing. So we're going to have more of a hyperbolic shape. This is a different type of conic section where we can have in the C1 direction an increase, but a C2 direction a decrease. And this is what we call a saddle point. It's shaped kind of like a saddle. You move to the sides of the saddle and it slopes down. You move to the front or the back of the saddle and it slopes up. As kind of a side note here, that turns out to be important for some of your homework and some of the later derivations. There's a property of symmetric matrices that asserts that a matrix A, a square matrix A, is orthogonally diagonalizable if and only if it is symmetric. That is, if it is equal to its own transpose. And this is known as the spectral theorem. The spectral theorem is quite important here, and there are a number of different results emanating from this theorem that are quite important for later derivations. So an orthogonally diagonalizable matrix can form an orthonormal eigenbasis. This means that the eigenvectors of such a matrix are orthogonal, not just linearly independent. So we can think of cases where maybe we have some eigenvectors that are linearly independent, but they're not orthogonal to each other. So if we have a symmetric matrix and it's orthogonally diagonalizable, then the eigenvectors of such a matrix are orthogonal. And I mentioned earlier that a matrix used to define a quadratic form is symmetric. You can go through and try and convince yourself of this, maybe try to find a counterexample. But because all matrices that are used to define quadratic forms are symmetric, the corresponding eigenbasis of such a matrix is orthonormal. Also, the eigenvalues of a symmetric matrix are always real. In other areas of mathematics, other applications of linear algebra, the case of an imaginary eigenvalue is really quite important. If we are thinking about dynamic systems, for example, if we are looking at the case where we have some kind of harmonic oscillatory response, that corresponds to the case where we have imaginary eigenvalues. But here, our eigenvalues are always real. If we are talking about eigenvalues corresponding to matrices that are used to define quadratic forms. And if these eigenvalues are always real, all these things we've been talking about the last several minutes really are general. These real eigenvalues allow us to have this common geometric interpretation or understanding of quadratic forms, and this just holds in general. But this geometric interpretation that we've been talking about, so for example, the magnitude of an eigenvalue tells us something about the steepness of a function in the direction of the corresponding eigenvector. That's not really going to make sense if we are dealing with complex eigenvalues. But because quadratic forms always involve symmetric matrices, we don't have to worry about this. The eigenvectors are always real. When we looked at some of these earlier examples, we saw cases where in some directions the function increased very rapidly, and then other directions it did not increase very much. And there are different ways of describing this. If we're thinking in terms of the level sets, we could talk about the ellipticity of the function. Or in one direction, it's barely changing. Another direction, it's super steep. And this has a lot of impact on how difficult a nonlinear optimization problem is to solve. And if we have a quadratic function where the level sets look pretty circular, if the minor and major axes are similar in size, then we're going to have an easier to solve optimization problem. But if it's highly elliptical, if the major axis is far larger than the minor axis, or in other words, if one of the eigenvalues is a far larger magnitude than the other, then we're going to have a nonlinear optimization problem that's much more difficult to solve. And when we get into the numerics of this, it's going to become more clear why it's so difficult to solve. So we have a way of quantifying this property of a nonlinear function. If we look at a nonlinear function and fit a quadratic model to that nonlinear function at a point, and then we look at the properties of that quadratic function at that point, we can do some analysis on it. We can look at the difference in eigenvalues, and the ratio of the largest eigenvalue to the smallest eigenvalue magnitude. That's going to give us some great insight into how difficult this problem might be to solve. We're going to define something called the condition number. Given a matrix A, and if we evaluate all of the eigenvalues for that matrix A, and we look at the magnitudes of those eigenvalues, and we identify what's the largest magnitude eigenvalue and what's the smallest magnitude eigenvalue, if we compute the ratio of the largest to the smallest magnitude eigenvalue, that gives us the condition number. I should give a side note, this is actually a simplified definition of condition number. There is a more complete definition of condition number that involves singular values, and that's not something that we're covering in this class. So for the purposes of this class, you can think of condition number as being this ratio of the largest to smallest magnitude eigenvalues, but be aware that there is a more general definition of condition number. So if you go on to other topics where we deal with matrices with different properties than we are here, then there's more to learn. If we have a condition number that is equal to 1, then that means that the steepness in the steepest direction is equal to the steepness in the flattest direction. And that's going to give us very circular looking, or if it's equal to 1, it's going to give us exactly circular level sets for our quadratic function. So the closer to a condition number of 1, or the closer to circular level sets that we have, the easier a numerical optimization problem is going to solve. are going to be to solve. But if we have a condition number instead that is much larger than 1, this is what we call an ill-conditioned optimization problem. It's really difficult to navigate this problem, and in the next section, this next part of class, when we actually get into the optimization algorithms, we're going to go through a few different ways, looking at first unconstrained and then constrained optimization, and we're going to see exactly why this increases the computational expense for gradient-based optimization methods. So one way of visualizing this, if we have a condition number that's much larger than 1, then we're going to have a valley in our function where in some directions it's going to be very flat, in other directions it's going to be very steep, and if we have this high ellipticity, then it's going to be a hard problem to solve. So as an aside here, for completeness, it's not a big focus of this class to know how to solve for eigenvalues and eigenvectors analytically. You do need to know how to do it, but it's more important that you have a deep understanding of the meaning of eigenvalues and eigenvectors. So let's suppose we have a matrix A, and we have, using the techniques we described earlier, using the characteristic equation formed using a determinant function, we have obtained all of the eigenvalues. We have not yet talked about how do you get the eigenvectors. Well, one way of doing that is to form this following linear system of equations. We take the original matrix A, we subtract a known eigenvalue, and then we multiply it by an eigenvector. And this eigenvector is unknown. Well, this is a linear system of equations of the form ax equals b, where vi is the unknown, and then we solve this system for vi. We repeat this procedure for all of the different eigenvalues, and then we can get the eigenvectors. Of course, pay attention to cases where we have a repeated eigenvalue. Of course, it's going to give us the same eigenvector after that. If you really just need to get the eigenvalues and vectors numerically, then in MATLAB you can just use the EIG, the eigenvalue command, and it'll solve for it automatically and very quickly. We have one final topic to go over in this section on linear algebra. If you have in your linear algebra course covered this topic of quadratic forms, you've probably seen this before. So suppose we are looking at a matrix A that is used in the definition of a quadratic form, or a quadratic function with only quadratic terms, no linear or constant terms. And we're going to look at three possible cases here where we could have a quadratic form with this particular property, where no matter where we move from the origin, so for all values of x, for all vectors that are in the space Rn, and remember this quadratic form, it's centered on the origin, and we can think of moving or defining any value x as taking some step away from the origin in some direction. So this first case deals with no matter what direction we move, the function f of x, or this quadratic function, strictly increases. And that's a rather special property. We have an infinite number of directions that we could be looking over, an infinite number of x values that we could be looking through. And that's quite a big property to show, to be able to say definitively that no matter what direction we move, we are always going to increase this value. Well, it turns out that we already have the ability to prove what must be true for this to occur. I'm going to introduce a term first, though, and describe this matrix A as what we call positive definite. So this is kind of like a greater than symbol, but it's a little bit curved, and sometimes it's used to denote when a matrix is positive definite or negative definite. And so here in this class, I'm using this symbol, this way of expressing that a matrix A is positive definite. So that means we have a function, this quadratic function, that looks like a bowl of some sort. It's concave up. And the origin is a minimum. And we want to be able to know when we can guarantee that these properties hold. So that's case number one. That's a positive definite matrix. And then number two, it's the opposite. If no matter what direction we move, the quadratic function decreases, then we say that this matrix is negative definite. But then there's one other possible case, and that's this mixed case. If there's at least one direction where we can move, there's at least one vector x such that we can decrease the function value, and there's at least one direction, a different direction, where we can increase the value, then we have what we call an indefinite matrix. Or in other words, the quadratic function f of x, it increases in some directions, but decreases in others. And we've already geometrically described what this case looks like. This is a saddle point. If we are thinking about a saddle on a horse, if we're thinking about the direction off to the side, the lateral direction, the saddle slopes down. So it's decreasing in some directions. But then if we think longitudinally, then the saddle increases in height in other directions. So that's where the term saddle point comes from. And if we look at the level sets of such a function, a quadratic function where the underlying matrix is indefinite, the level sets of f of x, these are going to be hyperbolae, not ellipses. Let's go through and see how we can tell whether a matrix is positive definite, negative definite, or indefinite. So suppose we're looking at a positive definite matrix. If we have this case, no matter what direction we move, the function always increases. In other words, x transpose ax, which we derived earlier is equal to c transpose dc, is always 0 for not only any x value, but also for any c value in Rn. And remember, we can define f of x as being equal to c1 squared lambda 1 plus c2 squared lambda 2 plus cn squared lambda n. So that means this increases in any direction. So no matter which of these coordinates we choose, if we move away from the origin, then f of x increases. Well, how is this going to happen? If any of these eigenvalues are 0, we're going to be going flat in the corresponding direction. If any of the eigenvalues are negative, we're going to be going down. So in each of those cases, that violates this initial assumption for a positive definite matrix. So what's the only thing left? What's the only possibility left? It means all of the eigenvalues are strictly positive. If we have a matrix where all eigenvalues are strictly positive, we can assert that it is positive definite. And then no matter what direction we move away from the origin, the corresponding quadratic function is going to increase. This is a really powerful result that allows us to make a general statement about an infinite number of directions from a finite number of eigenvalues. And it's this sort of result from linear algebra that gives us the power we need to derive optimality conditions for general continuous optimization problems that we can then use either to solve problems analytically or to derive numerical algorithms that can help us find solutions. We can also make a similar argument for negative definite matrices. This corresponds to the case where all eigenvalues are strictly negative. And then in this case, the indefinite case, we have at least one eigenvalue that's negative and at least one eigenvalue that is positive. So going back to the geometric intuition here regarding the sign of the eigenvalue telling us whether we're going up or going down, well, that corresponds exactly to how we discussed a saddle point. So eigenvalues are a really powerful tool for understanding the shape of quadratic functions. They're going to be really important for understanding optimality conditions. A thorough understanding of these topics is required for gaining the intuition that you're going to need to understand the nature of continuous nonlinear optimization problems, optimality theory corresponding to these problems, as well as solution methods. So I encourage you to make sure you understand these topics well. Go back to your linear algebra textbook if you need to, fill in these gaps, and then we can move forward with confidence in optimality theory. One quick aside as well, I've talked about positive definite, negative definite. There's another term called either positive semi-definite, positive or negative semi-definite, and that is the case where we allow for flat spots, where these eigenvalues could be zero. And some of our optimality conditions involve these positive semi-definite matrices. Okay, well, this is the last topic I plan to cover for a review and introduction to linear algebra topics as related to this course on engineering design optimization. Thank you.